Okay, awesome. Okay, so good morning. So there's one sort of final topic from chapter 3 that we're going to cover, which is the theoretical yield. I talked a little bit about theoretical yield. I kind of described what it is, but let's look at an actual problem in theoretical yield. So I'm going to pull up this problem here, and let's share this. Okay, so this is called theoretical yield of chemical reactions. So in this particular question, they give you something called aqueous sulfuric acid, H2SO4, reacting with solid sodium hydroxide, NaOH, to produce aqueous sodium sulfate, Na2SO4, and liquid water. What's the theoretical yield of water formed from the reaction of 34.3 grams of sulfuric acid and 21.0 grams of sodium hydroxide? Round to 3 significant digits or figures. Actually, I say figures here. So in a sense, we did that problem yesterday. The wording was a little different. It would give you the amounts of the reactants and then asked you to find I think it had to do with water. I think we were doing a reaction where you formed water, and it asks you for the mass of the water that was produced. This is exactly the same thing. The theoretical yield is just what would you calculate the mass of a product to be, okay? So it's really the same idea. So let's start by translating these words into an equation, into a chemical equation. So we're going to take sulfuric acid, H2SO4. That's going to be one of the reactants. Solid sodium hydroxide, NaOH, that's the second reactant. And it's going to produce aqueous sodium sulfate, which is, formula is given, Na2SO4. And then the other product is given H2O. Okay, so 2 reactants, 2 products. What is the theoretical yield of water? Okay, so how much water are we going to form if we're reacting 34.3 grams of sulfuric acid and 21.0 grams of sodium hydroxide? So let me stop share. Oh, sorry, it's up here. Go. There we go. Okay, so we'll start with the equation. The reactants are H2SO4. It's aqueous, so we put AQ. It's reacting with sodium hydroxide, NaOH. Solid. Okay, that's forming aqueous sodium sulfate, so that's Na2SO4. And that's also forming water. Okay, so there's your equation, but remember, we have to check to see if this is balanced. So I'll balance it in a moment, or check anyways, but I'm going to write the masses down. Okay, so those are the masses there. But we have to balance the equation, right? So there's a couple of different ways to balance this equation. You've got hydrogen in 2 reactants and 1 product. So that's, a little tricky to figure out what to do with the hydrogen. The sulfur is relatively easy because it's only in 1 reactant and 1 product. So if you take a look at the sulfur, you've got 1 on each side, so that's fine. The oxygen, look at oxygen, it's everywhere, right? It's both reactants have oxygen, both products have oxygen. So that's a little tricky too. The hydrogen and oxygen are sort of the tricky parts there. Sulfur is pretty easy. But take a look at the sodium. That's the 4th element, right? You got hydrogen, sulfur, oxygen, and sodium. Sodium, there's 1 on the left and 2 on the right. So that's easy to fix. If you've got 2 on the right and 1 on the left, just put a 2 there, and now you've got 2 on the left. So now we've got the sulfur balanced, right? One on both sides. Sodium's balanced, one on both sides. I'm sorry, two on both sides. Now we can kind of go at that hydrogen and oxygen. So if you take a look on the left side, we've got two hydrogens here. So there's two. And then we've got another two there. So that's a total of 4 hydrogens, right? Now there's no hydrogen here, so that's not a problem. There's 2 here, so let's put a 2 there, right? So by putting a 2 there, now you have 4 hydrogens on both sides. So 4 hydrogens, that's good. Now let's do the oxygen. 4 oxygens here, another 2 here, right? So that's 6. You got 4 here and another 2 there. So that's 6 there. So the oxygen is done. Okay. So it's actually not so bad. As long as you do the sulfur and the sodium first and leave the hydrogen and oxygen till after you work on them, it's relatively simple. Okay. Pretty simple equation, actually. Now, let's get down to the issue of the theoretical yield. What is the theoretical yield of water? Okay, what's the theoretical yield of water? Really, that's just another way of asking what is the mass of water produced? Okay, because the idea is that one of these reactants is called a limiting reactant. We don't know which one it is yet. But we do know the limiting reactant is either going to be H2SO4 or it's going to be NaOH, right? The limiting reactant is one of the reactants. And then you've got this other thing called the excess reactant. And again, we don't know which one it is yet, but we do know it's either H2SO4 or NaOH, okay? The limiting reactant is the one that gives you the lesser product. The excess reactant is the one that comes out to give you more of the product, right? Really just the mass of the product. Now, they could have worded this, they could have said, hey, what's the theoretical yield of sodium sulfate? So they want to know the theoretical yield of water, but there's also a theoretical yield of sodium sulfate. They could pick either one, okay? So here's what we said yesterday. What we said was, what you do is you just go through a chain of calculations. You start with the mass of your first reactant. And then you convert that to moles of that reactant. And then you convert that to moles of your product. In this case, it's water. And then you convert that to mass of your water, right? So you do that one. Of course, the way you convert mass to moles is you divide by the molar mass of H2SO4. You use the balanced equation. There's 2 moles of H2O for every 1 mole of H2SO4, right? So you're going to multiply by 2 over 1. I won't put the units in there, but we have to use units. And then you convert moles of water to mass of water by multiplying by the molar mass of H2O. Okay, so you do that for the first one. So let's do it. Let's, instead of writing out the flow chart for the second one, let's just do it for this one. So your mass of H2SO4. Now, H2SO4, its molar mass, if I'm remembering correctly, it's around 98.08 or something like that. So let's see, you got 2 hydrogens and 1 sulfur, and then you got 4 oxygens. So yeah, I get 98.09. So remember, you divide by the molar mass. So 1 mole over 98.09 grams. So notice with this one, I'm not writing the chemical formula H2SO4 out. You can write that out, or you could, leave it out. But really, we're talking about grams over grams. That's the key point there. The units are going to cancel. So 34.3 divided by 98.09, and you get under a mole, right? Okay. Second step, we're trying to figure out how much water we have. So the relationship is every time 1 mole of this reacts, you get 2 moles of water. You get twice as much water out, okay? So we take our 0.34968 moles of H2SO4, and then it's 2 moles of water for every 1 mole of H2SO4. It's kind of cool. So times 2. So you get 0.69936 moles of water. Okay. And then convert that to grams. The theoretical yield is typically the mass in grams or kilograms. It could, in theory, be in moles. You could leave it in moles, but usually these problems are going to want to have it in grams. So 0.69936 moles of water. And I'm just going to multiply it by the molar mass of water, 18.02 grams per mole, right? H2O, 2 hydrogens, 1 oxygen. You look those masses up, and then you get it. So times 18.02, looks like I get about 12.6. Okay, so that could be the theoretical yield. It's essentially a 50-50 proposition. The theoretical yield is going to be either from the first reactant or the second reactant. It is possible they match up perfectly. So if you get exactly the same mass from both reactants, that's what's called stoichiometric reactants. They're matched to give you exactly the same number. But typically, one will give you more than the other. The reason for that is materials can be expensive. So if you're reacting something that's very expensive with something that's very cheap, sulfuric acid is probably more expensive than sodium hydroxide, but I'm not sure. So if one is more expensive, you don't want to lose out on any of the more expensive reactants. So what you'll do is you'll make the expensive one the limiting reactant, and the cheaper one the excess reactant. That way, if there's any unreacted substances, it's the cheaper one. Okay, so these are actually both materials that are produced in huge amounts. These are huge industrial compounds, sulfuric acid and sodium hydroxide. Okay, so there we go. So there, we'll do the second one now. The second one, we're going to do essentially the same thing, but we're going to do it with the second reactant, the sodium hydroxide. So 21 grams sodium hydroxide. We talked about it yesterday. When you calculate sodium hydroxide, it comes out to 40 grams per mole, 40.00. So you have 21 over 40, which is 0.5250 moles of sodium hydroxide. Then the relationship is you have 2 of these for every 2 of those, right? So you take your 0.5250 moles of sodium hydroxide, and it's 2 moles of water for every 2 moles. Now, some people will just write 2 over 2. Like they won't actually put the units in, moles of H2O, moles. They just say, look, it's a 2-to-2 ratio. So just multiply it by 2 over 2. And that's perfectly fine. You can leave those units out if you want to. So, 2 over 2 is 1, right? So when you multiply it by this, you get the same number, 0.5250. And then we're right at this step here. Once you've got the moles of water, you know how many moles you have, just convert it to grams, multiply by the molar mass. So 0.5250 moles of water times 18.02. Okay, so times 18.02. Looks like you can get around 9, right? It looks like around 9 grams, 9.46. I rounded it to 3 significant digits. You got a smaller number, right? This one's smaller. This one's larger. So that means this is the answer. This is the theoretical yield. Okay. The theoretical yield is 9.46 grams. And we can also, even though the question didn't ask for this, we can identify the sulfuric acid, the H2SO4, that we started with 34.3 grams, that gave us the larger value. So that means it's not all going to get used up. So the excess reactant is the H2SO4. The reactant that gave us the smaller number is the limiting reactant. So the limiting reactant would be sodium hydroxide. Okay. Like I said, it didn't ask for that, but that's how you would identify. Okay. So if they were doing this in a way that, you know, from an industrial perspective, where you take cost analysis as engineers, then what essentially would have happened is the sodium hydroxide is limiting. So it's probably the more expensive reactant. You want the more expensive one to be the limiting reactant. Okay. In terms of industrial compounds, sulfuric acid is the largest industrial compound in the world in terms of what's produced. They produce more sulfuric acid in factories than anything else for chemical reactants. Okay, it's used for all kinds of things. It's not easy to get it. Oh, you can get it though. There are hardware stores that will sell sulfuric acid. It's pretty nasty stuff, but they will sell it. Okay. All right, any questions on that one?
Just that, Professor. So you're saying that the H2SO4, that you said that would be the excess, right?
Right.
Because it has more.
So the excess one is the one that would give you more of the product. So since the H2SO4, see how we started here with H2SO4, it gave you more of the water. That tells us the H2SO4 is the excess. And that number right here, it's actually not a good number. It's not real, meaning that we're not actually going to produce 12.6 grams. We can't produce 12.6 because we will run out of sodium hydroxide before we get up to 12.6. So that's why we don't use this number for any of our calculations. It's a number you would get if the sulfuric acid was the limiting reactant. But since it's the excess reactant, you can't really get. So in the end, you'll have some left over. You'll have some leftover sulfuric acid, and we'll only get 9.46 grams of the water. Can't get 12.6.
Okay.
If you remember the analogy of the pizza, essentially if you had all these breads, all these doughs, but not enough of the toppings, you would have some leftover dough. And it's the same thing here. We would have leftover sulfuric acid in this particular reaction. Okay. But it's not obvious. You can't, you know, I mean, you might be able to say, well, wait, that's a bigger number. So maybe that's going to be the excess reactant. This one's smaller. So that's maybe going to be the limiting. You have to be very careful about that because I could, you know, I could increase this up to, you know, 31 grams. And if I made it 31.0 grams, that would raise this up to like probably around 13 to 14 grams. So even though this number here is smaller than this one, in that case, this would be the limiting, you know, this would be the result. We'd get 12.6 grams instead of 13 to 14 because you always pick the smaller number. So be careful. Don't assume the reactant that has a lower mass necessarily is the limiting reactant. It could be, but you don't know for sure until you go through these calculations. So a lot of steps there, right? So, you know, review it, look it over a couple of times, try it, see you get the same numbers. And, you know, that's about as involved as it gets in this chapter. You know, because there's a lot of steps in that. Let's see. Yeah, what's the theoretical yield? Okay. Good. So that's it. So that's the theoretical yield. So now that pretty much ends chapter 3. We've gone through everything in there. I didn't talk really about percent composition, but that's the first calculation. Is pretty simple actually. So if you can do these ones, you can do percent composition very easily. So our next topic is moving into a little bit of what Sophia was talking about earlier in terms of chemical reactions in water. So we're going to get into that at this point. So let's start by calling this chapter 4. Which is reactions in aqueous solution. Okay, so if you remember, we sometimes use this notation where we put parentheses AQ after the chemical formula. This means aqueous, and it means nothing more than dissolved in water. That's what it means. So we wouldn't put this, I'm sorry, we wouldn't put this because water is the liquid. This is the liquid that things dissolve in. And the liquid that things dissolve into is called the solvent. Okay, the solvent is the liquid. So it's liquid water. So if you have pure water, it's a liquid, it's not aqueous. Aqueous means you're dissolved into the water. Okay, so aqueous is used to describe what are called solutes. And these are the substances that dissolve into water. Okay, so what dissolves in water? We have actually, as children, you played with these kinds of things. You know that table salt dissolves into water, right? Table salt is sodium chloride. Okay, we know that. We also know that sugar dissolves into water. In fact, pretty much all types of sugars dissolve into water. So sugars, well, there's different types of sugars. There's this one, which is called glucose. Glucose is often added to Gatorade. So that's one type of sugar. There's also sucrose. This is a different type of sugar. That one also dissolves into water. There's also alcohols. They dissolve into water. So one of them is methanol. Oops, let me write the formula first. It's called methanol. And then there's ethanol. That also dissolves into water. So, some salts dissolve into water, like sodium chloride, sugars dissolve. Let's see, what else? Ammonia dissolves into water, right? So ammonia is NH3, that dissolves into water. And there are other types of salts too. So we're going to get into these a little bit later. Other salts. So there's table salt, which is specifically sodium chloride, but there's other salts too. KBr. I'm just giving a few examples. These are not ones that are particularly important. So KBr is a little bit like sodium chloride. It's got a metal and a non-metal. Barium. Is it barium sulfate? I guess it's barium sulfate. No. Barium hydroxide, sorry. So barium hydroxide, for example. Okay, that one dissolves in water. There's a bunch of them. Okay. So what we're going to do is we're going to kind of think of different categories of things that dissolve into water to form solutes. And so we have sugars, alcohols, ammonia, and then salts. Okay, those are sort of the things. We're going to talk about acids and bases as well, so we'll get into that. So let me bring up, to begin with, let me bring up a problem. Use my mouse. Okay. These are loading slowly. Okay. So this example says predicting the products of dissolution. So there's a lot of words in here before you actually get down to what you're dealing with. So let's take a look at it. The names and chemical formula of some chemical compounds are written in the first two columns in the table below. Okay, so if you look at that first column on the left, you've got, the names of the compounds. So methanol, magnesium sulfate. Sulfate is sometimes spelled with a pH, so Sulphate. Iron 3 bromide, which can also be called different things too. So it could be called ferric bromide. So if you ever see ferric, that refers to iron. Okay, so the formulas are written right there. Okay. We're going to assume that these are soluble in water. Now, the term soluble means they dissolve into water. So sugars dissolve in waters, alcohols dissolve in waters, and salts dissolve in water. So it says here, these are soluble in water. Imagine that a few tenths of a mole. So the reason they say a few tenths of a mole is they're saying we're not putting too much in there. We're putting a little bit. A few tenths means a little bit. Each of them is dissolved into a liter of water. You know what a liter of water is because you know what a liter of bottle is. Write down in the third column of the table the chemical formula of the major species. So what is going to form when they dissolve into water present in the solution? For example, water will be there, right? Because if you have a solution of water, there's water there. So make sure you start with water. And then write down the other ones as well. Now, it says major chemical species are those present in concentrations greater than 10 to the minus 6 moles per liter. What that means is there's some. It's not so little that it's a trace, contamination. So anything that you think dissolves, write that down, okay? I think in general, even though it doesn't say there, I think you want to separate them with commas. I think if you separate them with commas, the formatting turns out well. Okay, so let's talk a little bit about what it means to say that something dissolves into water. And in this process, I'm going to describe a little bit about the physics of how water actually dissolves things. There's great videos online in showing how salts dissolve and all that kind of stuff. So I'm going to show you my little crude pictures here. They're not going to be real fancy, but I'm going to give you an idea of what's happening here. And let's begin with the alcohols. So the first thing to say is that in general, alcohols are compounds that have a carbon attached to an OH group. That's essentially how we recognize them, okay? So for example, CH3OH, okay? Sometimes it's written this way. This is called methanol. And you have to be careful because we write things in different ways in chemistry. That can be a little bit frustrating, okay? if you see a carbon in the formula, and then you see OH, that tells you it's an alcohol, okay? So it could be written that way. It could be written CH3OH. This would be an alternative way to write it. But the main point is that you see a carbon in there and then you see an H. That tells you it's an alcohol. Alcohols dissolve into water. And here's how they do it. Water has an oxygen at the center, and the central oxygen is chemically bonded to two hydrogens, which are on opposite sides of each other. Well, not exactly opposite, right? They're not on opposite sides. They're kind of on the same side, but in a sense also on the opposite side. So this is what's called a bent structure. We'll get more into this at the end of the course. We really do all this kind of discussion of structure at the end of the course, so we're a little bit ahead of it, but it's important in terms of talking about solubility. So there's a bent structure here, and it looks like a V, right? You've got the oxygen in the center and then two surrounding atoms of hydrogen, and it's bent. And for reasons that we will go into in chapter 8, it turns out there is a small negative charge associated with the oxygen atom. Now that little symbol there is called delta. Okay, the negative is the charge. It's a negative electrical charge. And it turns out this negative charge is a pretty involved issue. Where does this negative charge come from? So we're not going to go into any of that right now. But the point is, for now, is that there is a small negative charge. So delta means, in this context, it means small. Okay, so there's a little bit of negative charge there. Likewise, there's a small positive charge in between the hydrogen atoms, right in the center, okay? And so this gives rise to a very interesting electrical property of water. It's called a dipole moment. Essentially, the water molecule behaves as though it were like a tube, like a hero roll or a stick with a negative end. Let me write it this way, actually. With a negative end and a positive end. So it acts like it's negative on this side and positive on that side, right? So negative down here, positive down here and negative over here. It acts like a little charged particle, okay? And like I said, we'll get into that later in the course. The effect of this is the following. When you take liquid water, so you have a beaker full of water, you've essentially got all these little water molecules bouncing around, colliding with each other, moving around each other, random movement, called a random walk. Huge numbers of them. They all have these little electrical charges associated with them. So in general, what they do is they form specific arrangements around each other. And the arrangements are, they try to minimize the case where negatives are near each other and positives are near each other, and they try to arrange themselves so that the negatives are near the positives, right? So you end up with these interesting little arrangements. There's an internal structure to liquid water. So what are they doing? They're trying to maximize the interactions between opposite charges and minimize the interactions between same charges, positive, positive, negative, negative. Remind yourself, if you have something that's positive, you get repulsion here, right? They fly apart, or they try to fly apart if they can. That's a repulsive interaction. On the other hand, if you have positive and negative, then they try to attract each other, or they will attract each other. But since water is a liquid, the molecules are able to move around. So even though they're trying to, get near each other in a certain way, they really can't because they're bouncing around. They have too much energy to stop. If you cool them down, then they will actually stop and form structures. We call that ice. So solid ice or solid water is the case where you've sucked all the energy out of it. So now these molecules can just sort of hold each other rigidly. Okay. Now what happens is when you put an alcohol in, the alcohol has this OH group. And the OH group is kind of like a water molecule. Water is H2O, right? OH group. In fact, the water molecule has two OH groups. Alcohols also have this OH group. So the alcohol, drawing it kind of crudely here, we can draw it sort of like this, CH3OH, which is kind of like, here's your OH, the O is negative, and the H is positive, and the CH3 is over here. The CH3 doesn't really have much in the way of electrical properties to talk about, so it's kind of neutral, but the OH does. So that means this alcohol has a negative and a positive, just like water does. So what will happen is the alcohol will orient itself relative to the water molecule. So I'll write CH3 there. So the negative end, which is the oxygen, and the positive end, which is the hydrogen, will interact in such a way. So this is your alcohol right here, right? So the alcohol actually, in a sense, is attracted to the water molecule. It has to rotate so that the negative end of the alcohol, which is the oxygen, is interacting with the positive end of the water molecule. And then likewise, you'll have interactions like here. There's a negative-negative interaction, a negative-negative interaction. Now notice there's a repulsion here, right? That's repulsion right there. So the water molecules will also orient themselves to maximize attractions and to minimize repulsions. So you end up with something that's kind of like this. You end up with the alcohol having all the water molecules orienting themselves with a positive, negative, positive, like that, right? And then the hydrogen, which is positive, the water molecules will surround them like that. So now you got all these water molecules surrounding the alcohol molecule. They will essentially drag the molecule around. And so now that alcohol is part of a mixture with the water. It makes what we call a solution. It is dissolved by the water based on the fact that it has this OH group. So in general, substances that have carbon and an OH, they will dissolve very nicely into water to make solutions. There are exceptions. There's always exceptions to everything, or to most things in any case. But in general, if it's an alcohol, it has that OH group, it will dissolve into the water based on these interactions, okay? As I said, at the end of the course is when we really get into a little bit more details of that, okay? All right, so alcohols dissolve into water. Now, when they do dissolve, they don't do anything except get attracted by the water molecules. So they don't change their structure in any meaningful way. So if you put an alcohol into water, it's still an alcohol molecule. It hasn't really changed very much. It's just that it's now attracted to the water. And that's an interesting effect, because what that means is if you have a bottle of alcohol and then you pour some of the alcohol into the water, it's true the alcohol is in the water, but its chemical properties are not going to change all that much based on being in the water. So it will still be an alcohol. So if we dissolve an alcohol, sorry, that's an H, CH3OH into water, what we will get is the mixture will have water in it and it will have the alcohol. So those are the two major components that you would get when you dissolve an alcohol into water. You get the water and you get the methanol. Okay. So if we look at that first, let's bring it up over here. If you look at this first part of the question, it says, hey, if you've got methanol, which is CH3OH, what are the major species dissolved in the water? Well, you put the water, right? H2O, that's going to be in there. But there's also going to be methanol. So CH3OH. You just write the formula for that substance. And that's how alcohols will work. There are other molecular or organic substances that dissolve into water. So for example, there's organic acids. They will dissolve into water too, but we're not going to deal with them at this moment. Now let's get down to these other materials. The second one is magnesium sulfate. It has a magnesium and a sulfate ion in it. And then we've got iron 3, so Fe, and bromide, which is Br3. So let's talk about those. That's a slightly different issue. So let's talk a little bit about what are called ionic compounds. And with this, we're really talking about ions. Ions are very interesting little species. It turns out you can take an atom. So this is an atom. And you can remove an electron from it. You can take an electron off of it. Now, the electron, which we will represent as an E with a negative superscript, E negative is an electron. If you take an electron off of an atom, what you're left with is a positively charged atom. And this is called a cation. All right, so a cation is what you get when you take an atom and you remove an electron. But you can also do it with a molecule. So for example, let's say we have H2O. So there's your oxygen and 2 hydrogens. So this is a molecule, right? H2O. You can also remove an electron from a molecule. And if you do, what you get is a charged molecule. So now, just like with the atom, it has a positive charge. So I'm just going to write a little positive above it, right? Okay. This is now an ion. In fact, it's a cation, right? I'm sorry, it's a cation. Cat means positive. Okay, ion means it's charged. So cation literally means positive charge. It's something that has positive charge. That's a cation. So you can make cations out of molecules and you can make cations out of atoms. Which atoms tend to make cations? Metals. Metals tend to form cations. Okay, so for example, lithium. Lithium is Li. It tends to form a cation. Okay, notice how I wrote the formula here. The symbol for the element is Li. The symbol for the cation is Li+. Another example, sodium, Na. The ion, the cation, is Na plus. And so if you see a plus, that means it lost 1 electron. Lost 1 electron. But some metals lose 2 electrons. An example of that is magnesium, Mg. It turns out magnesium is more likely to lose 2 electrons. So we write that as 2 plus above it. Mg 2 plus. This means it lost 2 electrons. Another atom that tends to lose 2 electrons is zinc. Zn. It tends to lose 2, so it's Zn2 plus. And some atoms will lose 3 electrons. An example of that is iron, Fe. Iron has a tendency to lose 3 electrons. Okay, so every time you lose 1, it becomes positive. If you lose 2, it becomes positive 2. If you lose 3, it becomes positive 3. So sometimes people will ask, well, can you get positive 4? And it turns out there are metals that can become positive 4. There are metals that can become positive 5. There are metals that can become positive 6. 7 seems to be about the limit. There aren't very many metals that can lose 7 electrons. That's a lot of electrons to lose. There's 1 or 2 that in theory can lose 7 electrons, but not very many. Okay, so metals tend to lose electrons. So where are the metals in the periodic table? They're in the first 2 columns. So lithium, sodium, potassium, rubidium, cesium. Hydrogen is not really a metal, but we do put it in that first column for various reasons. And we're going to call this column 1A. So those other than hydrogen, those elements are metals. Second column, beryllium, magnesium, calcium, strontium, barium. This is column 2A. Those are metals. So they tend to lose electrons. Then you get, in the middle of the periodic table, you get these metals over here. And these are called the transition metals. So they start here with scandium. So that's element 21, goes all the way over here to zinc. And these are a lot of the metals that you're familiar with: gold, silver, copper, iron, nickel, cobalt, chromium, a lot of those very common metals, okay? Silver, for example, well, copper is right there. Silver is underneath it. Gold is underneath that. There's a bunch of metals there. Okay, so those are metals. They tend to lose electrons too. And then you have what are called post-transition metals. So they come after the transition metals. So an example of that, there aren't very many of them that we need to worry about, but one of them is right here. It's aluminum, right? So you know about aluminum. You've used that metal many times in your life. There's another one down here called lead. PB, plumbum is lead. Plumbers used to use lead, so they're called, so PB. And then there's a few others as well, but these are the post-transition metals. They tend to lose electrons. There are a couple of patterns, and the patterns are these ones tend to lose 1 electron. These ones here tend to lose 2 electrons. But other than that, there's not a lot of patterns. The transition metals are hard to tell. Sometimes they'll lose 2, sometimes they'll lose 3, sometimes they'll lose 1, sometimes they'll lose 4. There's not that many patterns. There are a few though. One is, in general, aluminum will lose 3. Zinc will lose 2. And silver will lose 1. Okay, so I just recommend memorizing these three: aluminum 3, zinc 2, silver 1. They actually make like a little pattern here. So 3, 2, 1. So those three. And then remember that the first column, they lose 1, and the second column, they lose 2. So
This is
those
not
would,
always based on like valence electrons.
yeah, it's connected to valence. Exactly. It's connected to valence electrons. That's right.
Because some of them have configurations where they only like, I don't know, like I'm looking at zinc, for example, and it has 2. Oh, it does lose 2. Okay. So that makes sense. All right. Or like
Yeah.
aluminum like has like 1. So does aluminum also tend to lose 1?
So aluminum's right here. It loses 3.
Even though it has like only 1 valence electron? Am I reading that wrong?
It actually has 3 valence electrons because you have to count the valence electrons on the left side as well.
Oh, okay.
But yeah, we'll get to that. We'll get to that in chapter 7. I guess chapter 7. We'll get to that much later though. Okay. So for now, what we do is we treat it pre-electron knowledge. So before they knew about electrons, they just noticed that these elements had a charge of +1. So their charge is +1, right? If you lose 1 electron, you have a charge of +1. That's something you can measure. These ones have a charge of +2. And so the aluminum is +3, the zinc is +2, and the silver is +1. Okay. So metals form cations, which are positively charged ions. Now, what's the importance of why would we even go through this since we're not really covering, valence electrons and all that yet? The reason it's important is because of the structure of water again. Remember that water has a dipole moment. It has a positive end and a negative end. And if these metals form cations, they have positive charges. So for example, a sodium, it's in the first column, loses 1 electron, it has a positive charge of 1. So a sodium is actually much more likely to be positively charged than it is to be neutral. In nature, the sodium atom is actually very rare. It's hard to find sodium atoms. They tend to form sodium ions, sodium cations. So the result of that is that water molecules will be very strongly attracted to it. So I'm going to draw these little water molecules with their dipole moments surrounding the sodium ion. Now I'm exaggerating the sizes. These are not to scale. But see what the water molecules did? They orient themselves so that the negative end, which is essentially the oxygen atom, is oriented toward the sodium ion. Okay. So now we have all these attractive forces between the molecules of water and the sodium cation. So what's the result of that? It's just like the alcohol. The sodium ion will be dragged along by these water molecules. And that leads to an interesting result. If you have a compound that has sodium in it, so sodium chloride, for example, the water molecules are so strongly attracted to the sodium ions in the compound that they will just pull them out of the compound and drag them along into the solution. And so now their sodium ions are mixed into water. So when you put sodium chloride into water, it dissolves. You can see it dissolving, right? It disappears according to your eyesight. The reason is those sodium ions are being pulled out of the solid and dragged into the water. And then they are solvated by the water molecules. So what you'll end up with, it's kind of interesting. You'll end up with the ion being in the center. So there's your sodium cation. And then you'll end up with these water molecules forming layers around the sodium cation. So you get these different layers of water. I'm not drawing the positives and negatives in there just to save a little time. But you get like 3 or 4 layers of water molecules that are going to be surrounding that ion. So it's pretty hard for a sodium ion to move around unless, unless it has some water with it. So those water molecules will just essentially surround it. It's 3-dimensional. So it's more like an onion than it is like I've drawn right here. But you get these different layers of water molecules. And these are called hydration layers. Hydration meaning water, right? Hydration means surrounded by water. So you get these hydration layers of water surrounding the sodium ion. And so then the next sodium ion is actually going to be way over here. And it's going to be surrounded by these water molecules. Okay, again, you're going to have all these layers. I think it's estimated that if you have salt water, the number of water molecules surrounding a sodium ion is like, it's in the 20s. It's like 20 or something, like 20, 25. Huge number of water molecules per sodium ion. Okay. So that's what it essentially means to say that sodium is soluble in water. What it means is if you have a substance that has sodium in it, that sodium will be distributed in the water in the form of cations. And this gives it electrical properties. Now that you have this positive charge, or these positive charges, right? Those are the sodium ions. And they're surrounded by water. The water gives those ions mobility. So now those ions can move around. In biology, they move into cells and out of cells. So you have a bunch of water molecules bringing the ion to the protein in a cell membrane, probably releasing it into the membrane. And then when it comes out of the membrane, then a new group of water molecules will drag it back out into the cell. And the same thing happens just in a bottle of water that has salt dissolved into it. The sodium ions are bouncing around and being dragged along. It turns out these ions conduct electricity. So the reason that a swimming pool is dangerous in a thunderstorm is not because the water conducts electricity. It's because the ions like sodium that are dissolved in the water, they are the ones that actually conduct the electricity. But they're given mobility because they're in liquid water, which moves them around. Okay. So when we look at compounds that have these metal ions, so for example, the second one right here, right? Magnesium sulfate. See how it has magnesium in it? There's your Mg. Well, magnesium is in the second column, group 2A. So it's going to form a +2 ion. So what will happen is the magnesium will get dissolved into the water. So what we would expect then from, coming back, let me stop this here. When we have magnesium sulfate, is that magnesium, that's your metal. And you just go look in the periodic table, and what you'll see is that it's in column 2A. It's right underneath beryllium. It's right here, which means that it's really going to be Mg+2, right? Because that group 2A, they form +2 ions. So that means you've got a magnesium cation. This is called a magnesium cation. And so what will the water molecules do? Well, they'll surround it, right? I'll draw it a little smaller here. By the way, when you're writing charges, you write the number first and then the symbol, this, the sign, positive, negative. So the water molecules are going to hydrate it. In fact, they'll be even more strongly attracted to this one than they are to the sodium, because the magnesium has more electrical charge than the sodium does. It's +2 instead of +1. So those water molecules are really going to be strongly attracted to it, twice as strong, the interaction. Okay. Now, how do we write that in terms of symbology? What are the symbols for that dissolved in water? Well, we could write it this way. We could just write Mg2+. And how did I know it's 2+? Because it's in the second column, group 2A. That's what tells me the charge. Okay. So first column 1A +1. Second column 2A +2. Aluminum +3, zinc +2, and silver is +1. Okay. Now we could also write it Mg2+ and then put AQ after it. And technically this is more correct, because really it's not just Mg+2, it's Mg+2 in water, so we would write aqueous. I think when you do the ALEX problems, they just expect you to write this. I don't think they expect you to write the AQ, and that's fine. But strictly speaking, ions are not stable unless they're in water or in a compound. So magnesium sulfate, MgSO4, would be stable, but Mg+2 all by itself is not very stable. They'll react with something to get rid of that charge. Okay, so there's our discussion of cations. But what about this other side of the compound, the SO4? We have to deal with that as well. And it turns out that's another type of ion. So what we're going to do now is we're going to talk, I'm almost done. Sorry, we're running out of time. I just want to finish this problem. We're going to talk about anions. So the anions are negative ions, and they tend to be the non-metals. So for example, group 7A, fluorine, chlorine, bromine, and iodine. These ones are -1. That means they gained an electron. Group 6A, oxygen, sulfur, selenium, tellurium. These ones are -2, which means they gained 2 electrons. Group 5A, nitrogen, phosphorus, arsenic, antimony. These ones are -3. They gained 3 electrons. Those are really the 3 columns that we need to be concerned with. Those right there. Okay, so what's the notation? The notation would be Cl-. If it gains 1 electron, we just write a negative next to it. If it gains 2 electrons, let's do the sulfur. So that's in 6A, it's -2. So we write it as 2 negative. If it's in the group 5A, let's take P, for example. It gained 3 charges, so it's 3 negative. Okay, so Cl negative, S2 negative. Now these are anions. They're negatively charged, so we call them anions. Same thing. They are attracted to water molecules. Why? Because the water molecules can orient themselves with the positive end toward the anion, right? They just rotate. So that's the cool thing about water. It can be attracted to positive ions, but it can also be attracted to negative ions. All it has to do is rotate. Now, that's a problem if it's a solid. Ice doesn't dissolve salts very well because the water molecules are locked in, they're rigid, they can't move really. So if they can't move, they can't rotate to maximize the attractions. So for that reason, if you freeze water, the salts will actually form a separate layer. And so that's a way to purify water. If you want to get rid of the salts out of the water, freeze it. If you freeze it slowly, the salts will rise to the top into a different layer. And then the water that's actually frozen will be relatively pure. So here we go. We got all these positive, these are the water molecules, right? But what's happening is the positive end is moving there. So that means these anions can also be stable inside of water. So let's come back to this sulfate. Well, you might say, well, there's a sulfur there, so you're going to be S -2. There's a bunch of oxygen, so negative. It turns out this is called a polyatomic ion. And there are several polyatomic ions you should be aware of. So let me write a few of them down. Let me do it this way. So there's a few that have -2 charges. Here's a few that have -1 charges. And then here's a couple that have -3 charges. Okay. Now there's a bunch of them, but they don't give you too many in your homework assignment. So these are called polyatomic ions. I'll write it again up here. And the importance of this is that you want to recognize them in the formulas. So if you see MgSO4, what you want to do is you want to say, hey, you got your metal. So there's your +2 magnesium. And then you see SO4, don't break that up into separate ions. It's not a sulfur ion and an oxygen ion. It's SO4. So you come over here and go, oh, it's -2. So this one's -2. And again, because they're charged, they're going to be soluble in water. And there you go. So our answer then to that question would be, what are our species going to be in this MgSO4? Well, first of all, it would be water, right? Water is going to be in there. But now you've got your magnesium, which is in group 2A. So that's Mg2+. And then you've got your sulfate, which is right here, -2. Okay, so that would be the answer to that second part, which is if you have MgSO4 dissolved in water, what would be the major species? It'd be water, magnesium +2, and then sulfate -2. The last one they put in there was FeBr3. Okay, so what do we have? We have Fe. Now this is a little tricky because what's Fe? Fe doesn't have a specific charge that it has to be. It could have different charges. However, if you look at the question, they tell you it's iron 3. They give you the name also, which is a nice hint. When they give you the name, if it has Roman numeral 3, that means it's +3. So they're telling you the charge of the metal right there. If it were Roman numeral 2, that would mean it's +2. Okay, so you can use that. Okay, so we've got Fe +3. And then what about Br? You got Br. Now, notice there's 3 of them, but that's fine. That just means that because the iron has a charge of +3, you have to have 3 bromides to balance the electrical charge in the compound. Bromide is in group 7A, so it's -1. So the other species would just be bromide with a negative charge. You don't need to, if you're just saying, hey, what's dissolved in the water, you don't have to write 3 Br- or Br3-, just write Br-. That's the actual species that's dissolved in the water. Okay, so the answer then would be water, Fe3+, and then Br-. So those would be your 3 major species that are dissolved in the water. And the take home of this whole question, a lot of discussion for it, is that your alcohol They don't form ions. Right? So that first one, the answer would be water and methanol. Those are the major species. But it's just CH3OH. Alcohols don't form water. But the ionic compounds do form ions. So you get water and then 2 separate ions. And the same thing with the iron bromide. You get water, iron 3, and then bromide. Okay. So we'll talk more about this tomorrow. I'll do another example tomorrow so we can go over it, and then we'll start looking more at what are called precipitation reactions. Okay. Come over here.